All right, welcome back. This lecture is going to be about rotational motion. So things that, rotate or also turn. Turning is just rotating around an axis outside of yourself there. So yeah, let's get to it. Up until now, we really have only talked about motion in a straight line, like going left or going right or going up or going down. Talk about things falling, like if you release something, it drops, but it accelerates, but it just goes straight down. Or moving things straight along, or talked about like cars driving along, but driving in a single direction. So all of that there's a number of different terms for it, but generally speaking, you call it translational motion, meaning all you're doing is just changing the location of where an object is. So like if I have a ball and I release that ball, it just drops straight down. So all it's really doing is changing from being located up here to being eventually located down the ground. So the other kind of motion, well now we're going to talk about a bit, is not just if you change your location, but if you change your orientation. And so that's what we call rotational motion. And you can generally think about maybe splitting that into two kind of separate things, but it's actually just the same type of stuff. So there's a rotational motion where you're just rotating, like rotating around like yourself. Like if I start just rotating, I'm sort of rotating around. If I imagine like a line that goes vertically through me, I'm kind of just twisting around that line. Right? So that's a rotation. However, if that line wasn't going straight through me, if that line was, say, up and down right over here, and I changed my orientation on that line, it wouldn't look like me just turning around, it would look like me going around in a circle, right? So I would follow this like circular path around this axis. So whenever we're talking about rotational motion, it's always changing orientation. So you can kind of imagine that as, just straight rotating something around kind of itself, or turning, which is rotating around an axis outside of the object. So everything up until this point has basically just been translational motion. And one of the main reasons for that is, full disclosure, rotational motion gets tricky. Because now we're not just dealing with how, like when you talk about velocity, you just talk about the rate at which an object changes its location. How fast is it going from one place to the next. When we're talking about rotation, well, as you already kind of saw, if I wanted to describe a rotation, it's not just saying how fast is it rotating, because I also have to tell you where it's rotating about, right? Like me rotating around this kind of line that goes through me looks one way, but me rotating about a line over here would look totally different. And then me rotating around a line that would be like parallel or running sort of horizontally would look completely different. I would be doing like a sort of dolphin jump over it. So inherently rotational motion is complicated, and we're just going to spend some time today talking about it and some interesting consequences of what happens when you start rotating things. Rotations inherently deal with circles and circular motion. If you're turning, then you're essentially just reorienting yourself towards some point around a circle in a sense. And it's even more than that in that when you rotate it around an axis, if the axis is through me, then that's like one type of that rotation. But if the axis is further away from me, then the way that I classify how quickly I'm going around that axis depends on how far I am away. Right? Because if I'm really close to it and I walk at a steady pace, it's not going to take very long to go around that axis. But if I'm much further away and I walk at that same steady pace, so my velocity in a sense is the same, or the velocity we thought about before, is the same, it's going to take a much longer time to rotate around that axis. So once we start talking about circular motion or rotational motion, we have to start worrying about how far away you are from the rotation, or the axis of rotation. And the sort of thing that ends up happening is similar to how the sort of the circumference and the radius of a circle are related to each other, in that essentially the circumference and the radius of a circle are proportional to each other. So if the radius gets bigger, the circumference gets bigger. If the radius gets smaller, the circumference gets smaller. Another way of saying that or interpreting that is that the further you are away from the center of the circle, the longer it will take to get around, or the further you have to go to get around that circle. So when we're talking about circular motion or rotational motion, there's actually sort of two kinds of speeds we could talk about. One kind of the speed is just how many times you go around, you make a complete revolution, or so you go around that whatever axis you're rotating about, how many times you go around it completely in 1 second. That would be a rotational speed. So how many revolutions you make around that thing per second. So like your car, if it has, I'm going to get the name wrong, but it has a kind of meter on it, and we'll say how quickly essentially your engine is revolving around. And it's like in the thousands of revolutions per second. So that's telling you a rotational speed, how quickly it's going around this circle. It's quite fast. I think it's per second. I might be wrong about that, but essentially that's telling you a rotational speed. So the other kind of speed involved in rotational motion is tangential speed. And that is much more analogous to what we would have thought of as just velocity before, or a regular sort of speed. It's basically like how, it's the total distance you travel per second. So if I have to go around a circle, if I want to know what the tangential speed is, I just need to know how far around that circle is and how long it takes me to go around. I divide those two, I get a tangential speed. So it's much more similar or much more related to what we were talking about as velocity beforehand or speed beforehand. So the new sort of thing here is the rotational speed. Right? When we're talking about revolving, rotating, it's how many revolutions or how many times something goes around per second. Why does that matter? Why do we care about that? Or why is it even a thing? Well, if we imagine, say, these two kinds of, I don't know what they are, insects on a record player, right? And they're both stationary. They're not moving. They're not walking around the record player, but the record's just going to be rotating around. If they're both just standing there, but they're at different distances from the axis of the rotation, from the center of that record, then what's the difference in their rotational speeds? Do they have a difference in how many times they go around per second? Well, it says it right there. They don't actually, because the whole record is rigid. So essentially, if you think about just like one slice where or one like line where those bugs are standing, that line is going around, and it will go around. Each point of that line is going to go around once in whatever many seconds it takes to go around. Right? So the rotational speed of this thing is the same because it's all part of one solid object that's just turning. So all those pieces have the same rotational speed. However, since the bug on the outside is on a further distance from the axis of rotation, right, it's at a larger radius, that means the circumference or the distance it has to go around to actually complete a revolution is much longer than the one that's closer in. It's going at a further distance in the same amount of time. That means its tangential speed is higher, right? Because it's moving from one place to the next quicker than the one on the inside is. Right? So if you just imagine it rotating, the one on the inside is actually literally moving slower than the one on the outside because it has to go further, but it's following that same sort of arc, right? Because it has the same revolution or rotational speed. And just to be clear, that terminology I'll probably use multiple times. This is axis of rotation, and that's like a line that you're measuring the rotations about, right? So for the record player, it's like a vertical line that goes through the center of the record. So the whole record revolves around that. These little bugs revolve around that. Okay, so let's try a little question having to do with rotational speed. All right, so consider these two wheels or whatever you want to think of them as, gears or something. Maybe two gears on a bike, and they're connected by a chain here. Right? So these two gears, one's small and one's large. They're connected by a chain, and so when they're rotating, which wheel is going to have the higher rotational speed? Meaning, which one's going to go around more per second, make more revolutions, or go around more times per second. And by how much? well, I think it's meant to be that the radius or the distance to the edge of these gears is, say, 1, whatever you want to be, meter, inch, and then 2. So the bigger wheel has twice the radius as the smaller wheel. So twice the radius means also twice the circumference. Okay, so take a second and try to answer that, and we'll come back to it in a second. Okay, so these were kind of tricky, so don't worry if you didn't get a good answer, or you weren't able to get the correct answer here. But in this situation, since there's a chain that's connecting these two wheels, the chain is essentially forcing the tangential speed around the edge of each of the wheels to be the same, right? Because when the first red dot on the left moves up to the top, right, that's the chain moving that far. Looking over at the bigger wheel, the first green dot would be up at the top, and as the chain moves, it now moves over to the right. The chain moves just that amount on each of the wheels as it's kind of turning. And essentially what it comes down to is that since the chain forces each of them to go at the same tangential speed around the outside, you imagine those dots keep moving along, like the chain keeps moving along, and the smaller wheel has much shorter or much less of a circumference, shorter distance for it to go around before it completes a revolution. So, 2 or 3 more of those sort of dot evolving like steps later, the small wheel will have made a rotation, whereas the big wheel will have only gone halfway. So that's telling you that the small wheel is going to do more revolutions in a second, or it's going to rotate around its axis quicker. And then by how much? Well, I already said that the larger wheel has twice the radius, meaning it has twice the circumference. And then since their tangential speeds are the same, when the small wheel goes around once, the large wheel will have gone around half a way. So then the small wheel goes around again, the large wheel will have made 1 full rotation. Right? So the smaller wheel makes 2 rotations for every 1 rotation the large wheel makes. Or you could say, in other words, it has twice the rotational speed. Yeah, so kind of tricky. You have to think about this a bit. Yeah. And then quickly, I don't want you to worry too much about this, but so it should be pointed out that before we move on to talking about more details of rotation, we've already talked about regular translational motion, where you're just moving the position of an object. And now we're trying to talk about rotation, and you want to get sort of like into even more complicated things you could imagine is essentially if you combine both of those things, where an object is changing its location, but it's also changing its orientation at the same time. So, you compare this sort of like simple motion where you just toss a ball, and we haven't really talked about projectiles yet, we'll get to that. But if you toss a ball, it's just going to make this sort of arc and land. However, if you toss a bat, the bat tends to want to rotate around its axis, technically around its center of momentum, or center of mass. So when you toss the bat still does this arc sort of thing. The center of mass of the bat will do the arc, but the rest of the bat is going to rotate around it. So you have this combination of this rotational motion and translational motion. And there's a little video clip here. You can actually watch this happen. Like I said, I don't want you to worry about it too much. So if you're interested, definitely check out the video clip. It's just kind of cool. You can watch this. I think it's like a hammer or something that you watch it do this sort of interesting path where the ends of it are going crazy as they flip along, but the center of mass of the object is just staying still as it flies along. Okay, so just like in translational motion, one of the first things we talked about, one of the most fundamental things about translational motion, is the concept of inertia. And hopefully you recall that inertia is actually the property of mass that wants to resist any change in its motion. And the more massive it is, the more it's going to resist a change in its motion. So if you have something and it has mass, then it has inertia, and it's going to be difficult to either get it moving or stop it moving, or get it moving faster even too. So just an example, if you have a gold brick, it's much more massive than, say, a block of styrofoam. right? And so remember that the inertia of an object is just proportional to its mass, essentially. So the more massive an object is, the more inertia it has, the more difficult it's going to be to get it moving. So then in rotational motion, there's essentially the analogous property for objects when they're rotating or when they're going to rotate, that they have this property that they resist that rotation. They don't want to get rotating, they don't want to stop rotating once they're rotating. And essentially we can just call this rotational inertia. So you just throw rotational in front of it, in front of inertia, and there you go, we got rotational inertia. So just like regular inertia is essentially a measure of how difficult it is to get an object moving, get it started moving or stop it from moving, rotational inertia is a measure of how difficult it is to get an object to rotate. And again, since we're talking about rotation, it's a little bit more complicated in that we need to talk about or specify a specific axis of rotation. So like in the case of showing here, we have, say, a wooden bat versus a plastic bat, but they're the same size, the same shape, and we're trying to rotate about an axis that's going through like the handle of the bat, so that X is kind of, showing that there's an axis running sort of out of the image and into the image here, and we're trying to rotate these bats in this fashion. Right? So we say these objects have rotational inertia, meaning they resist, or they will resist if you try to start them rotating. And as it turns out, just like inertia is proportional to mass, rotational inertia is also proportional to mass, but there's more complications on it, and we'll get to that in a second. But in this case, at least I can tell you that even the same size, the same shape objects, the wooden bat's going to be heavier, it's going to be more massive than the plastic bat, so the wooden bat there is going to have more rotational inertia. Right? So for one thing, rotational inertia depends on mass still. So just like inertia depends on mass, proportional to mass, rotational inertia depends on mass. The more technical term for this is moment of inertia, but I'm going to try to use rotational inertia. If I say moment of inertia, forgive me for that. Okay, so a little bit more detail about rotational inertia. It's going to depend on, like I said, the total mass of an object. So the greater the mass of an object, the greater its rotational inertia. And in a way, it depends on how the mass is distributed about the axis that you're rotating, or that you're trying to get it to rotate. So that bat, it has a certain rotational inertia about the axis in that picture that was through the handle. If I try to get it to rotate about the center of the bat, then the mass is distributed differently around the axis. It's actually more uniformly distributed around the axis now. And it's going to have a different rotational inertia. So you can start to see why, when we talk about rotation, it's always a little bit more complicated. But yeah, there you go. And essentially, the further or the more asymmetric mass is distributed around the axis, whatever axis you're rotating about, the larger the rotational inertia is going to be. So it depends on those two things. And particularly, it's usually proportional to mass, directly proportional to mass, and proportional to the square of the distance of how the mass is sort of distributed around. It can be pretty complicated though. But again, just recalling that our rotational inertia is just telling you how difficult an object is to rotate about a particular axis. So let's try a little question about rotational inertia. You have these two situations of probably a ballet dancer. You just want to know which of those situations, A or B, will have a greater rotational inertia, right? So which one's more resistant to being rotated? So take a second, give that a shot. All right, well, hopefully you said it was B, and the reason being, well, remember rotational inertia depends on how massive an object is, but in this case, we're talking about the same person, it's just different orientations of their limbs, essentially. So the mass is the same in each of these cases. So then it comes down to how is that mass distributed? And essentially the more asymmetric or the further away mass is going to be distributed from the axis of rotation, the higher the rotational inertia of that object is, right? So in the case B, with the leg stuck out, you have more of that mass being distributed further away from the axis, to the side here. Okay, got a bit of a twofer in this one, where let's have a little demonstration of this rotational inertia, but also try to ask yourself a question, try to think which of these situations is going to be easier to balance. So you take a hammer and try to balance it either on the head of the hammer or the metal part of the hammer, where the handle is going up, or try to balance it from the end of the handle and have the metal part, the hammerhead, on the away from you. So when you say which of these is, or when I say which of these is easier to balance, that all comes down to the rotational inertia of the object. Right? So remember that a larger rotational inertia means that object is going to resist rotating more. So if one of these situations has a greater rotational inertia, then it's going to resist wanting to rotate, and it's going to be easier to balance. So this isn't exactly the same, but essentially this guy has like a long stick and uses a metal clamp, metal vise, to essentially act as like the hammer, or the head of the hammer. Right? So this situation is essentially taking the hammer with the hammerhead part down and trying to balance that. Yeah, and it's not easy to get it across in film, but you might be able to tell he's kind of having a difficult time. However, when he flips it over, significantly easier to balance this way. Which may seem rather counterintuitive. Right, so which of these situations is easier to balance? Oddly enough, it's going to be situation B. Right? When the hammer, the heavy part is away from you. The reason being is that, again, it's the same amount of mass. They're both rotating around an axis that's like kind of along the tip of your finger, so trying to rotate that. But the mass is distributed differently, and in the case A, much more of the mass is closer to the axis of rotation, versus B, more of that mass is further away from the axis of rotation. So when that mass is distributed further away from that axis, it's a larger rotational inertia, meaning it's going to resist rotating. It's going to be easier to balance. And feel free to try that out on your own. Okay, another little demo about rotational inertia is if you just take two circular objects, a disc and a hoop, and make them out of materials such that they weigh the same. It's the same mass of materials, so one's a heavier material than the other, and the circumference, the radius and the circumference are the same. So they're essentially almost the same objects, except that one is a hoop, meaning it's hollow. There's no inside to it. Same amount of mass, same radius, and one's a disc, so it's solid, but same amount of mass and same radius. So if you were to put these two objects on an incline and let them go, they're going to start rolling, right? So they're going to start rotating, and they're rotating about the center of the disc, each of the axis to the center of the disc. And the question is, which one's going to roll faster? Right? So the way you answer that is to say, well, which one has the higher rotational inertia? That one's going to be harder to rotate, right? So it's going to go slower. It's going to take more time for it to actually get rotating, and won't speed up as quickly. So which one of these, the disc or the hoop, has the greater moment of inertia? Right? So same mass, but one has mass, or one has that mass that's more distributed away from the axis. Oh, there you go. The disc wins. All right, so again, that same amount of mass, it's the same size kind of overall, but the hoop, all that mass is away from the axis, right? Whereas for the disc, it's all kind of distributed uniformly around that axis. So the hoop has the higher rotational inertia. It's going to be harder to get it to rotate. It's going to go slower overall. Okay, said a good bit about objects rotating. But what causes an object to rotate? Why do the hoops start rolling, or why does the hammer want to go fall to the side, that sort of thing? Well, if you think back onto just our regular linear motion, why does an object accelerate, or why does it get moving? Well, Newton's second law, at least, probably all of them, imply that it takes a force to get an object moving. Right? I have to apply a force. If an object's sort of at rest, I have to apply a force and I can get that object moving. Right? Or if it's already moving, I can apply a force and bring that object to a stop. So when we're talking about rotation, it's a very similar thing. You need to apply a force, but you can apply a force in many ways to try to rotate something, and only some of the ways actually cause an object to rotate. When you do apply a force and it causes an object to rotate, we call that a torque. So you apply a torque, just the kind of classic example is a wrench. You use a wrench to apply torque to a bolt so that you can turn that bolt, so you can rotate it. So essentially, if you want to apply a torque, then again, right, you need to apply a force, and you need to apply a force that's sort of tangential to the circle you want to rotate the object about. Right? So like in this case, if you imagine the bolt is like the center of a circle, you can draw a circle around it, then the force needs to be applied tangent to that circle. Right? So just like it's grazing the circle. Or at least some component of that force, some direction of that force needs to be going there. So a torque essentially, well, it will depend on a number of things, and that is the magnitude of the force you're applying, right? So like just imagine this picture, if I pull much harder, I'm exerting a larger force, a larger magnitude of force, I'm going to exert a larger torque. It also depends on the direction of the force, and we'll talk about that a bit more in the next slide. And also depends on what's called the lever arm. So the lever arm is sort of, in a way, it's the distance from the axis of rotation that you apply that force. So if you know what the lever arm is, and it's not always strictly the distance from the axis of rotation to where you apply the force, again, we'll see some examples in the next slide. But if you know what the lever arm is and you know how much force you're applying, then the torque is strictly that force multiplied by that lever arm. Distance, the lever arm in a distance, so it might be meters or something. And the force, again, hopefully you know by now that the force we talk about in newtons. So that is to say the torque would be a newton meter. So just a little bit more about lever arms. And this is another topic that I think you should know about, but I don't want you to worry too much about it for test-taking purposes. But, right, so if you want to figure out what the lever arm is for a torque, it depends on, well, how far away from the axis of rotation you're applying a force, but also in what direction. So if you apply a force that's essentially perpendicular so in the far right, in the middle case here, we're applying torques that are strictly perpendicular to that distance from the axis of rotation, right, or a 90-degree angle. So the center picture in there is kind of the standard picture that we just saw in the last slide, right? So this, when it's perpendicular like that, that's our lever arm. Or when another way of looking at it again is when that force is tangent to the circle that we're trying to rotate about. So you can increase the torque by just increasing the lever arm, right, and still applying your force at that tangential direction. So this is the reason why if you are working on like automobiles or anything like that, and you can't get a bolt to move, it's stuck or something like that, you generally take some kind of pipe of some kind and put it on your wrench so that you can extend the length of that wrench, and what you're doing is you're extending the lever arm, right? And remember, the torque is just directly proportional to the lever arm, so the longer the lever arm you have, the more torque you can apply, and you can break that bolt loose. So what happens if you apply a force that's not tangent to that circle, right? So for instance, in the upper left picture, the force is being applied upward, but also kind of to the right a little bit. Well, if you want to figure out what the lever arm is, essentially you just extend the force kind of draw a dotted line along the same direction the force is until you hit a line that's perpendicular to that axis of rotation. Right? So in the upper left picture, you extend our force up and down, then eventually you're going to come down the bottom here and hit the kind of you can imagine it's like a radius that you're drawing away from that axis of rotation. We're going to want to hit it at that 90-degree angle. So what happens, or the effect of that, is that the lever arm that you have is actually shorter than it would have been if you acted your force tangent like this, right? So, and a similar thing happens if you try to act a force sort of on the inward angle. Again, you just kind of extend the force until you hit a radius drawn from that axis of rotation, and there you go, that's your lever arm. And again, that lever arm is going to be shorter than it would have been if you applied the force the tangent angle here. And then the last thing to say about this here is that, well, hopefully it's obvious by now that the optimal way to apply a torque is to exert a force, and that force should be tangent to the circle you're trying to rotate about, right? So that's like the upper, or the middle and the upper right pictures here. So the left and the bottom one, right, are both kind of suboptimal. Some of that force that you're applying is not causing any kind of rotation, so it's a wasted effort in a way. Okay? And the extreme case is, if you look at the upper left one, you know, I'm trying to pull on that wrench, and if I keep going, sort of dipping down the angle of that force I'm trying to pull on, eventually I get to the point where I'm horizontal, and I'm essentially just acting a force that's going away from the axis of rotation. Right? So in that case, then I'm just going to, well, I just end up pulling the wrench off of the bolt. Right? There's no way I'm going to rotate the bolt by acting a force in that way. And similarly, on the bottom left case, if I continue kind of arcing that force in towards the axis of rotation or towards the bolt, right, then I just kind of keep pointing in and in and in, and my force is doing less and less of a torque, and finally it's pointing directly at the bolt, which means you're essentially just pushing at the bolt, and again, you're not going to ever rotate that bolt at all. So this is all telling you that if you want to act a torque, you can act a force in a number of different ways, but at least some of that force needs to be perpendicular to that, or tangential to that circle you're trying to rotate about. A little check for yourself on torques. So looking at each of these pictures, just which of those will be exerting more of a torque. And the arrows are indicating the direction the force is being applied. And again, they're vectors representing the force, and they're the same length, so it's saying there's the same amount of force being applied in both of these cases, and the direction, well, they're both down actually too. But they're trying to apply torques in different fashions. So which one of these would you say is applying or exerting a greater torque? Hopefully you said situation A, right? And there's a lot of ways to look at it as to why that is the case. One is to just look at figuring out the lever arm, because the force is the same, so whichever, remember, torque is just force times the length of the lever arm. So whichever one has the longer lever arm is going to be the greater torque. In the case of A, right, so you're pushing on the bicycle pedal, you're trying to get it to rotate around this circle, and that force is exactly in the direction that's tangent to the circle, right? So the lever arm, or your force is already at a 90-degree angle to like a radius that you would draw from that axis of rotation, right? So your brakes, basically that's the maximum amount of torque that you're going to put on this bicycle gear. Right? Versus in the second picture, you're exerting a force downward, and it's almost going directly towards the axis of rotation. So if I were to try to figure out what size the lever arm was, it's going to be very small because I extend the force, right, and draw a dotted line, and it's going to go where it's going to run into a radius from that circle. It's going to be, if I draw it and it goes further down, it's going to hit at a 90-degree angle, almost right next to the axis of rotation. So the lever arm in case B is just a tiny little thing, right? It's almost nothing at all because you're almost acting the force directly to the axis of rotation. Okay, and then one more thing about torques, in that just as forces can balance out, right? You can like have multiple forces acting on something, and in the end, you get zero net force, meaning the object's not going to accelerate, or it's not going to start moving, or it's not going to slow down or speed up or anything like that. In the case of rotational motion, if you balance the torques, then the object is not going to rotate. And so how do you balance the torques? Well, a torque is, when you act a force and it causes something to rotate. So a torque is also, as you might have guessed, a vector. And so if I rotate something in one direction, right, there's a certain amount of, a certain magnitude of that torque, but it also has a particular direction. You could say it's clockwise or counterclockwise. That might be the easiest way of saying it. So if I act essentially a torque to rotate something clockwise, but I act an equal amount of torque to rotate it counterclockwise, then those torques are going to balance each other, they're going to cancel each other out, and the thing's not going to rotate at all. So like in this situation, where you have like a seesaw, and you have two people on either side of the seesaw. One's a bit heavier than the other. Maybe you got an adult and their child or something like that. So if I want to know what amount of torque each of them is exerting on that seesaw in order to try to rotate it, well, nicely enough, the force that they're acting is already tangent to the circle, or tangent to the circle that that seesaw would rotate around. So the lever arm is just the distance they are away from the center of the seesaw. And the force that's acting is the force of gravity. It's the force of gravity trying to pull them down. So if the child is 250 newtons and is 3 meters from the axis of rotation, then the torque they're exerting is 250 newtons times 3 meters is 750 newton meters of torque. And that would be in a counterclockwise direction, right? Versus the adult here, they're 750 newtons, but they're only 1 meter away from the axis of rotation. So the torque that they're exerting is 750 newtons times 1 meter is 750 newton meters of torque. So they're actually balanced, right? There's 750 newton meters of torque trying to go counterclockwise from the child, and 750 newton meters of torque trying to go clockwise, right? So there you go, they balanced each other out. There's no net torque on the situation, and it's going to stay balanced. And then even in the case if you were to, for some reason, hang the child off of the seesaw on a swing or something like that, does not look like it's a safe situation. But if you were to do that and nothing else changed, then it turns out this situation is still balanced. Why? Because the force that is trying to rotate this seesaw, particularly to rotate it counterclockwise, the force that the child is putting on it, is still acting at the same point because she's just hanging from the thing. So her weight is still pulling down at that 3 meter distance from the axis of rotation, and it's pulling down tangentially to the circle that rotation would happen. So each of these situations is actually balanced and would not rotate. All right, so now we're going to move on, or not move on, but yeah, I guess in a way, from strictly rotating an object about its axis, or about an axis through the object, to objects more generally turning, right, or moving in a curve. Because again, this is another kind of rotational motion. You're always changing your orientation around something, and you're moving around an axis. So there's a lot of things that do this. So this another instance of circular motion, like the car going around taking a turn, or well, if you just have like a thing and a little object at the end of a string, then you can twirl that thing around on a string. Right. Another example of this circular motion. And so these objects are following a circular path. And as it turns out, if you ever want an object to continue following a circular path, there needs to be a force that's acting on the object and that is pointed towards the center of that circle that it's turning around. So in this case, you have a car that's turning, say, around a corner here. You can imagine that turn is part of a larger circle, and and the center of that circle is off over here, so there's a force that is causing this car to turn, and it's pointed towards the center of that circle. And so we call this a centripetal force. And centripetal means a center-seeking force, so it's a force pointing towards the center of the circular path that the object is taking. So what is the centripetal force on this car? Well, let's just think about that. We'll get to it in a couple slides. Okay, so if an object's going to rotate in a circle, there needs to be a force pointing towards the center of that circle, and we call that force the centripetal force. Right? So here you go. I have just a little piece of a pipe on the end of a string, rotating it around in a circle. Is there a force on this object? Hopefully. And what causes that force? And in what direction is that force? You can just note down A, B, C, or D what direction you think the force is in. Right? Well, technically, that picture is showing the object spinning around horizontally, more like this. But yeah, so take a second, try to answer those questions. Hopefully they're simple, but maybe not, and we'll get to them in a second. Okay, so hopefully you said yes, there is a force. This is exactly what I just told you about in the last slide. There needs to be a force in order for this object to keep moving in a circle. So what is causing this force? Well, in the case of the thing that I'm holding right now, and in the picture here, the force on the object is from the string, right? The string's attached to the object, and as it's turning around, say like up here, there's a force, the tension of the string is pulling on the object, and it's pulling it towards my fingers, towards the center of the circle that it's rotating about, right? And by extension, that tension is also coming from my fingers, right? So I'm constantly, in a way, I'm constantly sort of tugging at this little pipe here in order to keep it going in a circle. And I'm always constantly pulling towards myself or towards the center of that circle. And well, hopefully that kind of gave away the answer to the last one, in that the direction would be A in this picture, right? It's the tension and you're pulling the object towards your fingers, which is the center of the circle that this thing's rotating around. Okay, so some examples of centripetal force, right? The last slide we just looked at is if you have an object at the end of a string and you just twirl it around, then the string is what's acting or playing the role of the centripetal force, or the tension specifically in the string, is pulling on the object, and it's always pulling towards the center of that circle, right? In the case of your car, right, your car is making a turn, it's going around some part of a circle, larger circle you can imagine, and in fact it's actually the friction between the tires and the road, and the friction is actually acting as a centripetal force. It's pushing towards the center of that circle that the car is turning around, and that's what's causing this car to turn. Well, another example is a satellite, right? So satellites just orbit around the Earth in these great circles, and what force is acting towards the center of the circle, towards the center of the Earth, is the force of gravity. Right? So the fact that satellites will go these circular paths around the Earth, and they do that because there is the centripetal force, in this case, or in that case, the force of gravity. So we'll see a little demonstration of the centripetal force, and more specifically what happens when you stop acting as centripetal force. Well, you might know if you stop that centripetal force, the object's going to stop going in that circle. So in the same way, where if I had my little piece of pipe rotating around, if I all of a sudden went and put a knife in the way, a very sharp knife, cut the string, the pipe's not going to continue going in a circle, right? What's going to happen is actually, if you think about it, the velocity of that object, of this little object right here, at any given moment, its instantaneous velocity, right? Like right up here, it's moving that way. Right, right up here, it's moving down. Up here, it's going that way. Right over here, it's going up. Right? So its velocity is actually always tangent to this circle that it's going around in. Right? So right at the top, it's going here, over here, then over here, over here. And it's that centripetal force that's acting perpendicular to that velocity that keeps causing the velocity to change its direction in order to cause it to keep moving in that circle. One way of seeing this is if you put just like a marble or some kind of ball inside of a hoop that's not quite a complete hoop but has a section cut out of it, you roll the ball or the marble in that hoop, right? The marble is going to roll around in a circle, and the support force here, the centripetal force is actually the support force between the hoop and the marble, right? So just remember, like if you press against a surface, there's a support force that pushes back. So in this case, the marble is going to press against the hoop, but the hoop is going to push a support force back, and that support force is going to be the centripetal force in this case that's going to cause this marble to keep moving in a circle. Except when it hits that open segment, no more centripetal force, the marble is just going to keep going in this tangential path, right? Like if you were to just draw a line that barely touches the circle right there, or along this point, that's the direction the marble is going to keep going. There you go. Well, that was quick. So it's getting its centripetal force, no more centripetal force. Now it just continues going in that tangential path there. So just quickly on more detail about the centripetal force and how large a centripetal force is. Well, the centripetal force is related to a number of different things about objects that rotate. So again, just think about this little piece of pipe that's hanging from the string, and if I rotate it around, the amount of centripetal force, or the tension in this string, the amount that I'm going to need to continue pulling on it, is going to go up if, well, for one, if I increase the speed. If I want to go faster, then I have to exert more force. I have to increase the tension in the string, and you can feel that if you do it yourself, right? It takes a little bit more effort. Slow back down, less force that I have to act. It also gets larger if the mass is very large, right? So if I want to keep it going at the same speed here, but I put an extra 10 pounds on the end of this string, then that's also going to cause it to be a larger centripetal force to keep it going in that same kind of motion. With a larger mass means it's going to be a larger centripetal force. And you can imagine that, just think like I have this little piece of pipe and I'm rotating around at this rotational speed. Nice. But then imagine putting a 100-pound weight on the end of that. If I wanted to keep going around in this same fashion, you could probably imagine that it's going to take a lot more effort to do that. And then finally, the centripetal force actually goes up as the radius being the distance the object is away from that center, goes down. Yeah, so the smaller the radius, the larger the centripetal force needs to be, right? And, well, that's also another one that's fairly easy to see. Like if I go for a very tight, very short radius that I'm going to try to swing this thing around, right? Get it going at a certain rotational speed, it takes a decent amount of effort. And then if I let a lot of that string out, and I want to keep going that same sort of speed, it's just much less effort, right? So when things are rotating even closer and closer to the axis of rotation, you need to have a larger centripetal force. That also comes up when you're, say, in a car and you're trying to take a turn. If you take a very tight turn, then you feel the reaction essentially to that centripetal force being more, and then you get pushed out to the side. Final thing we're going to talk about for rotation is the analogous thing to momentum. Right, so the whole last lecture, or maybe 2 lectures ago, we talked about momentum, which is just the quality of an object because it's in motion. So if an object has mass, it's in motion, then it has momentum. And we also saw a lot about if you want to change an object's momentum, then you need to act impulse on that object. And we had this conservation of momentum, where if an object had momentum, it wouldn't change unless there was some external force or something that came in, some impulse that came in, right? Or even a system of objects. Their collective momentum wouldn't change overall unless some external thing came in to act force or impulse. Okay, so that kind of momentum is what we would call linear momentum or translational momentum. Essentially, momentum having to do with motion in a straight line. And remember, momentum was just the mass of the object multiplied by its velocity. Now, we're talking about rotations, so there's a thing we can call rotational momentum. The more technical term is angular momentum. having to do with angles, changing angles. But the angular momentum of an object is very similar to momentum in that it's the object's rotational velocity, not just its regular velocity, but its rotational velocity, multiplied by the object's rotational inertia. So how difficult is that object to rotate? Remember, rotational inertia has to do with how massive the object is and how that mass is distributed about the axis of rotation. So mass up in the linear momentum case is essentially a measure of its inertia, linear inertia, and now we just switch over to the rotational case where rotational momentum has to do with rotational inertia and rotational velocity. And just as in regular momentum or translational momentum, it's conserved when there's no external forces coming in to act on an object. In the same way, rotational momentum is conserved when there's no external torques that act on a system. And this has some very, useful, but also just kind of fun consequences too. We're going to see some of those in a second here. The last thing to point out here is that just like linear momentum, or just regular momentum that we had before, was a vector quantity, so it has a certain amount and it pointed in a certain direction. Angular or rotational momentum is also a vector quantity. It's a certain amount and it has a directionality to it. So one of the interesting sort of places where rotational momentum, and particularly the conservation of rotational momentum, plays out is for like ice skaters who are spinning around. And by changing how their mass is distributed, by putting their arms in and putting their arms out, legs in, by changing how that mass is distributed, they can change their rotational inertia. But since their overall rotational momentum needs to stay the same, that means the rotational velocity has to change as well. In the case of like a ice skater, if they start out spinning like the picture on the left, where their arms are out, a leg is out, right? So they have their mass and their butts sticking out too. They have their mass distributed away from the axis, right? The axis is sort of right vertically through here. Then more of the mass distributed further away from that axis of rotation means a larger rotational inertia. And they're spinning, right? They have some rotational velocity, so they have some angular or rotational momentum. Sorry, if I say angular, same thing as rotational. But yeah, so they start out spinning like that with a large rotational inertia. When they bring their arms in and they bring their legs in, what they're doing is they're decreasing their rotational inertia, right? So in this equation at the bottom here, when the rotational inertia goes down, since the rotational momentum needs to stay the same, that means the rotational velocity needs to go up, right? So this is how conservation of our rotational momentum works, right? One of those things, rotational inertia goes down, that means rotational velocity needs to go up in order to compensate. So that rotational momentum overall remains the same, it stays constant. So that's why once the skater starts bringing their arms and their legs in, they start spinning faster and faster and faster. Basically, I'm just going to try to show you that demonstration where I'm going to start out spinning around in a circle with my arms out so that I have a larger rotational inertia. And when I pull my arms in or put them to my side, I'm going to decrease my rotational inertia. But since my overall rotational momentum needs to stay the same, and that means that my rotational velocity needs to increase. And I'm going to start spinning faster. And you can't see it, but I just have this little rotating platform here. It's nice and greased up, so it spins very freely. Get on it. Right? So I can spin myself around. Hopefully this is in frame. I don't know. I hope so. Okay, so start out, arms out, spin myself around. Let's see how this goes. And when I bring my arms in, the thing to notice is, do I spin faster? Or put them out, do I slow down? Yeah? Hopefully you saw that. Let's try that again. Come out, slow myself down. Speed myself up. Well, this whole thing kind of slowing down once in a while too. But hopefully you get the idea there. I think some of these other demos work a little bit better. But if that wasn't convincing enough, then just go watch a video of an ice skater do the little spin thing, it's very obvious then. Okay, so I have a couple of other quick little demos here. So another way to demonstrate the conservation of rotational momentum is if I stand on a platform that can rotate, and I hold an object that can also rotate in it by itself, like a bicycle wheel, then, well, essentially, let's just see. So I got my bicycle wheel, right? And if I stand on this platform, the platform can rotate, the bicycle wheel can rotate, and it doesn't even need to be up and down like this, but you got to remember that rotational momentum is also a vector quantity. So I can change rotational momentum by changing the direction or the orientation, the way that an object is rotating, right? So essentially, if I spin this bicycle wheel like this, that's one rotational momentum. And if I just turn it, I change this rotational momentum. So just by having something spinning and kind of rotating that, turning that thing around, that's a change in its rotational momentum. So what's going to happen is if I do that while I'm on a wheel that can spin it itself, is since its rotational momentum is going to change, and me and the bicycle wheel and this rotating platform, we're all sort of one combined system, when its rotational momentum changes, that means my rotational momentum is going to change to compensate. So what's going to happen is if I start spinning this guy, so I got him spinning, he has some rotational momentum, and if I turn him, it's going to want to change my rotational momentum. Da-da-da. Change its rotational momentum, change my own. Right? So all that is the conservation of rotational momentum. Right? This has some rotational momentum right now, and if I try to change it, then my rotational momentum is going to change in the opposite way, or to compensate for that. One other way, this might even be the simpler one to say to begin with, actually, maybe I should have started with that one. Again, this thing can rotate, the stand can rotate, so that means I can rotate. If I just stand on this rotating platform with my bicycle wheel, but none of us are rotating, then there's zero rotational momentum right now. And we're this like kind of isolated combined system right here. But if I start spinning this bicycle wheel, well, what just happened? This thing now has rotational momentum, but just a second ago, there was no rotational momentum. So what does that mean? That means I need to gain some rotational momentum to sort of counter it. That will be in the, the opposite rotational momentum, so that those two together, the wheel and me, are going to still be zero rotational momentum. Ooh. Oh, that's another one too. If it's already spinning, and I stop it, then that's again another change in rotational momentum. It's going to change my rotational momentum. Try that one more time. So no rotational momentum, and once I spin this, I'm giving it rotational momentum, which means I need to gain some rotational momentum in the opposite direction to compensate. It starts doing it, but I think this platform has a bit of friction, so it slows me down. But hopefully you get the idea, right? Conservation of momentum means if something's rotational momentum changes, then something else needs to have a change in its rotational momentum to compensate. And the final thing I'll show you, which is kind of cool, it has to do with how, all of this has to do with how gyroscopes work, but this is more obvious, where if I take this bicycle wheel, right now it's not rotating, so it has no rotational momentum, but if I started rotating, right, now it has rotational momentum, and it doesn't want to change that, right? It wants to keep that rotational momentum constant. So even if I hold it off on a string here, it's going to stay upright, because gravity is actually pulling down. Gravity is trying to act as torque to change this orientation of the rotational momentum, but it's not enough to really do much because it's a lot of rotational momentum. I can act as torque and actually change it, or change it back. but I have to act enough of that torque to actually affect the change. Otherwise, it has its angular or rotational momentum, and it just wants to stay constant. Eventually, the bicycle is going to stop rotating around. It's going to no longer have any rotational momentum. Okay, well, hopefully most of those demos were within the frame here. Yeah, I guess I'll find that out later. But those are some fun things to do. Like I said, rotation, some fun stuff can kind of happen with rotation. But it is complicated. So, hopefully that was interesting and informative. And if you have questions, hope to see some of you at my office hours eventually. Yeah. But that's all I got for rotation. So have a good night, or a good morning, or good afternoon, or whatever the case may be for you.